This webcast discusses the process of dimensional analysis. Dimensional analysis is a useful tool for analyzing or checking the relationship between variables to see if we have the right equation that describes that relationship. Dimensional analysis depends on something called the principle of dimensional homogeneity. That principle says that any valid equation must have the same dimensions on both sides of the equality. So the dimension on the left-hand side of that equation must equal the dimension on the right-hand side if it is a valid equation that shows a valid relationship between the variables. There is also something that is closely related to this principle of dimensional homogeneity, and that's the fact that whenever you add two quantities, they must have the same dimension or the same units. Checking for dimensional homogeneity is commonly used as a sanity check to test whether derived equations are plausible. So most physical quantities can be expressed in terms of combinations of 5 fundamental dimensions. Those fundamental dimensions are mass, length, time, electrical current, and temperature. For an equation to possibly be valid, the dimension has to be the same on both sides of the equality. And so there will be two ways that we'll use this process. The first is to confirm that the relationship between the variables is valid. Now, this confirms the basic relationship between the variables. For example, this variable is proportional to the square of this other variable. But it does not confirm the value of any numerical constants. And another practical use for this dimensional analysis is to find the dimension of physical constants. Let's look at a few at the process and then at a few examples. So the basic process for performing dimensional analysis, the first step is that you replace every variable in the equation with the dimension of that variable. The second step is that you ignore any numerical constants. Remember, a dimension is a physical characteristic that can be measured. Numerical constants, they are numbers and they have no tangible physical dimension. So you can safely ignore any numbers as you perform dimensional analysis. The third step is that you treat those dimensions algebraically. You simplify the equation, try to get it in the simplest terms possible using the normal rules of algebra, and then you compare the dimension on the left to the dimension on the right. If those dimensions on both sides are the same, then there's a chance that that equation is valid. Now, of course, you have not really confirmed or validated any of the numerical constants, but you have validated that the relationship between the variables makes sense. So let's look at an example. Let's say that you're taking a test and it's asking you to calculate the distance that an object that is starting from rest moves in time t, and you're unsure of the equation. You think that the right equation to use might be one of the following two that are listed here. Maybe position x equals 1/2 velocity times time squared, or maybe position equals 1/2 acceleration times time squared. And so we're going to use dimensional analysis to figure out which one of these equations is valid. So at this stage in our class, you may not know the dimensions of variables, and they will always be given to you. So in this problem, x, position or distance, has a dimension of length. T, or time, has a dimension of time. Velocity has a dimension of length over time, and acceleration has a dimension of length over time squared. You don't need to memorize these dimensions. They will always be given to you in our problems at this point. Okay, so now we're going to do dimensional analysis on both of those equations to see which one might be valid. Now the first one says position equals 1/2 v times time squared. So I'm replacing each variable with its dimension. The dimension of the variable x is length. Okay, so that's what we've got on the left-hand side. On the right-hand side, we have 1/2 vt squared. Now the 1/2 I completely ignore. That's a number. Numbers don't have a dimension. Okay, but the dimension of v, velocity, is L over t, and the dimension of t, time, is t. Okay, so I have L over t times t squared. Now I simplify both sides of this equation. So on the right-hand side, I have L over t times t squared. One of those t's can cancel with the t in the denominator, right? We've got t squared in the numerator, t in the denominator, and so I end up with a dimension on the right-hand side of length times time. That does not match the dimension on the left-hand side. Therefore, that first equation cannot be valid. But let's check the second equation. Again, I first replace each variable with its dimension. And so on the right-hand side, acceleration is L over t squared, and the dimension of t squared is t squared. I have ignored the 1/2 because that's a number, and we ignore numbers for this purpose. So now on the right-hand side, there is a t squared in the numerator and a t squared in the denominator. Those two things cancel, and so we do end up with a dimension of L on the left and a dimension of L on the right. Therefore, that second equation, it could be valid. Now, we have not really confirmed with this analysis that that 1/2 is the correct numerical constant, but we know that the relationship between the variables is probably valid.